Okay, welcome, Wednesday.
Yeah.
I'm glad to see everybody here because today's a really important day. Today we finally get to term symbols. So we did electron configurations last time. We looked at the data that justified our claims that half-filled subshells are stable, fully filled subshells are stable. One electron past either one of those is really easy to ionize, and so that explains the chemistry of the alkali metals. We didn't really talk about electron affinity, but that's sort of the halogens. You know, they like to complete that shell and become like a noble gas, and so they're really easy to reduce, to donate electrons to. And so then today we talk about the spectroscopic term symbols. So we're going to be talking about a lot of ridiculous, confusing nomenclature. Now, I didn't make this up. Otherwise, I would put different letters for everything. But we have case-sensitive terminology today. All right, so pay attention. We have little l's, which talk about individual electrons. And then we have capital L's, which talk about the angular momentum of the atom. Okay. And then we have little s's, which are the spins of individual electrons. And then we have capital S, which is the total spin for the atom. But then we also have capital S, which is also a term, which indicates the angular momentum. So it's all context-based, and it's case-sensitive. So you have to wake yourself up, okay? I know it's 8 o'clock in the morning, but we've got to pay very close attention to the context. And so when you're looking at all of the calculations today, be thinking, okay, that's a lowercase l, and it fits in this situation. That's the angular momentum for a particular electron. And it gives me these large capital L's, which are the angular momentum for the whole atom. And that can be a capital S, okay? And then when I'm talking about little s's, that's the spin of individual electrons. Those add up to capital S, which is the spin for the whole atom. And that's different than the term symbol S. Okay, so let's dive in. Now the need for these term symbols will be shown first, and that's the Grotrian diagram. This was the hydrogen atomic spectrum. Remember, the intensity of a spectroscopic transition is related to three things: that Boltzmann distribution, which gives you the thermal population, and then the I, that's the integral, that transition moment integral, and then G was the line shape, the Gaussian type line shape, if it's a normal distribution. And so this emission spectrum for hydrogen only exists when hydrogen is hot enough to have basically ionized, and then when electrons come back to that ionized proton to make a hydrogen atom, then they drop down through the various electronic orbitals, the various atomic orbitals. And so as they drop down, they emit light. And so these were three spectral lines in the visible spectrum for hydrogen, and this was the one spectrum that just totally wrecked classical physics. Okay, they couldn't explain this because this is something simple. This is a positive charge and a negative electron. They should be attracted to each other, but they had discrete transitions, and they couldn't explain these discrete transitions. So back at the beginning of the course, we talked about the scientists trying to explain the hydrogen spectrum, and this is what they were looking at, trying to figure out why we had discrete transitions. And de Broglie said maybe it's standing waves in these orbitals, and Bohr had that atomic model for the atom as like a solar system where the electrons were in discrete orbits. And the discreteness was the standing wave idea from de Broglie. And then Schrodinger took that standing wave idea and added in wave mechanics, and that's where we got quantum mechanics. So this is a very important spectrum. Well, if we put this in a broader spectrum of infrared, visible, and UV, we see a bunch of different lines. And these were just named by the scientists that published them. So we have the Balmer series, which is in the visible. We have the Lyman series, which is in the UV. And we have the Paschen series, which is in the near infrared, and the Brackett series, which is in the mid infrared. So these are all different series of lines, and they correspond to electrons dropping down from, say, the 4 to 3 level, or 3 to 2, or 2 to 1. Putting this in a slightly different diagram, if we rotate those transitions to 90 degrees, if you will, then we have the energy differences on the y-axis, and we now have an energy level diagram. So the Lyman series is going from these higher levels, like 5, 4, 3, and 2, all dropping down to 1. So that corresponds to the Lyman series. The Balmer series was all of these dropping to level 2. That's the one in the visible region. The Paschen is in the infrared. Okay, where all of these are dropping down to n equals 3. Now Rydberg and colleagues were able to fit these lines to these integers. They discovered quantum numbers, but they didn't understand what the quantum numbers indicated. They didn't really come up with the idea of quantum energy states. They just thought, this is strange that these spectral lines all fit differences in a series of integers. So it's a pretty interesting mathematical trick that they used. Okay, but they didn't understand what they were discovering. They were discovering quantized energy states. And so these initial considerations, we've shown in the past notes an energy level diagram that had the energy levels of the individual orbitals, like the energy level of a 1s orbital and a 2s orbital. But now in Grotrian diagrams, that's not what we're showing. So this is an important consideration for you to think about. We're showing the energy levels of the whole atom. So every energy level on here has a different electron configuration. So it's a single atom that we're talking about, like Mercury or sodium, but every level is a different electron configuration. There's only one ground state electron configuration, and that's typically what we teach you in the freshman chemistry. And that's what we talked about last time with the chromium, how chromium, the ground state is that 4s1 3d5. That's the most stable, that's the lowest energy one, so that's the ground state electron configuration. But think about it, you could have a bunch of different electron configurations. You could pair those electrons up in the d orbitals, you could excite some to p orbitals, and so on, and those would all have different energy levels. And that's what's being plotted in a Grotrian diagram. So here's the Grotrian diagram for hydrogen. And you can see the differences in the energy levels are given by all of those different arrows. And this is also the simplest Grotrian diagram. You just have one electron. And up here at the top, you have the angular momentum quantum number, S, P, D, and F. So that's L equals 0, 1, 2, and 3. Going up, this is N equals 1, N equals 2, N equals 3, and so on. And so the different electron configurations for this would be 1s1 or 2s1 or 2p1 for each one of those levels. Notice how the principal quantum number is unrestricted. Okay, so it could be, and we can change from delta n can be plus or minus 1. So it can go from 2 to 1, but it could also go from 3 to 1 or 4 to 1 or 5 to 1. But there does appear to be a restriction on the angular momentum quantum number changes. So these are selection rules in this diagram. Notice how the blue arrows all go either left one column or right one column. So we're seeing the selection rules here. We don't have a D to S transition, because that would be a change of 2 in the angular momentum quantum number. And so because this angular momentum is conserved with the angular momentum of light, we really just jump from adjacent columns. We go from an s orbital to a p orbital, or a p orbital to a d, or a d to an f. We don't jump from an s all the way to an f, because that would require 3 units of angular momentum, and light only gives you 1. Let's go to a little more complicated Grotrian diagram. Here's helium. Now that we have 2 electrons, they can be spin paired or spin unpaired. And if they're paired up, even in different orbitals, they're still paired up, that's a singlet. And if they're unpaired in different orbitals even, that's a triplet. So we have 2 sides to our Grotrian diagram in this case. We have the singlet states and we have the triplet states. So we need to designate that, and we see up here in these columns, no longer is it lowercase s, p, d, and f. It's capital S, capital P, capital D, and capital F. And then we have a superscript in front of that of 1s or 3s. So these are the singlet states. So this would be the singlet P. You have the singlet and the P. So that's the singlet P state. This would be the triplet P. So when we're talking about singlets or triplets, we're looking at that superscript that precedes the term symbol. So if I see a 3 up there, I know it's a triplet. How many unpaired electrons do I have? And that's helium. Just think about the context. Work your way through it. So that triplet comes from this 3 is equal to 2s plus 1.
They're both the same spin.
Yeah, and so this s comes from little s1 plus little s2. It's 1/2 plus 1/2. Right, so that gives you 1, a total spin of 1, and then it's 2 times 1 plus 1 gives you 3. But you could just look at that multiplicity and just subtract 1. That's how many unpaired electrons you have. So if you have a triplet state, you subtract 1 and you have 2 unpaired electrons. If you have a singlet state and you subtract 1, you have 0 unpaired electrons. If you have a doublet, you subtract 1, you just have 1 unpaired electron. Sometimes you can have quintets. Subtract 1, you have 4 unpaired electrons. Okay, so think about a d4 system all spin up. You got 4 electrons in the d orbital. That'd give you a quintet. Okay. So that's a little bit about understanding how we write the term symbols. Notice also we have another selection rule that we see in this Grotrian diagram. So what I'm trying to get you to see is just looking at the diagram and seeing the allowed transitions, and from that pulling the selection rules out. So let's look. It looks like N is unrestricted, even in a multi-electron atom. How do I know that? I'm looking here that this is all coming down to this ground state configuration, which is 1s2. Okay, and this would be the 2p. So it would be 1s, let me write that again. 1s, 1, 2p1. And this would be the 3p and the 4p. So I'm going from 2p down to 1s2, 3p or 4p, so I can have multiple jumps of n. Okay, so the n, the delta n, is unrestricted in terms of selection rules. But do you understand what I'm talking about when I'm looking at the Grotrian diagram? What about L? I still have those selection rules of plus or minus 1 L, 1 angular momentum unit. So I'm going from S to P, I'm going to adjacent columns, or P to S. And so those are allowed. We see all of these lines that jump left or right, 1 column. I can go from D to P. Over here I can go from S to P or P to S or D to P and P to D. I don't see any things from the F's. It's just, they're just showing you some of the transitions. The F to D is allowed, okay? But in this diagram, they're just not showing you all of the possible transitions. Now, it doesn't show any jumps from singlet to triplet, and so that's forbidden. Okay, so singlet to triplet transitions are forbidden. And this is also pretty busy. If I were to try to write out all the electron configurations, it would get very cluttered. And so let's zoom in. And so here's the Grotrian diagram for helium. Same diagram, just expanded a little bit with all of the electron configurations put on each of the energy levels. So now you can really see each of those lines, those energy levels, is for the whole atom. And that atom has that electron configuration that's shown on the screen. This is probably the most important figure this morning in terms of understanding what an energy level diagram looks like for an atom. So we put it in columns related to the various term symbols, whether it be triplet or singlet, S, P, D, or F. And then each one of those has got the different electron configurations. And notice it's just taking the ground state configuration and moving one of those electrons to some other orbital. And then that's your new excited state. So like right here, this one here, I've got an electron in the 1s orbital, and then I've got the 2s, the 2p, the 3s, the 3p, the 3d, and I've got an electron up there in the 3d. And it should be down because it's a singlet, so it should be pointing down. So those electrons are still paired, but it's been excited up to the 3D. Reactions to this? Any questions about this diagram that you're curious about? Yes?
So you said that 1s, 2s just got excited to 1s, 3d, so...
Yeah, so it's it may have done it in multiple steps, or it may have been an ion and an electron came down and is in that 3D orbital. But somehow this atom got excited to that electron configuration.
Okay, so this one isn't using light?
You can, you'll find excited state atoms from a number of ways. Like you might have in a combustion flame, reaction chemistry is happening, and then you have this helium atom that was ionized. It was a helium plus cation, and an electron came in, and now that electron is in the 3D orbital, and it's spin paired with the one in the 1s orbital, and so then you have that electron configuration. Or you could hit it with 2 photons of light. You could excite that electron to the 2p and then excite it to the 3D. So there's many different ways of getting an electron in that configuration.
Is it paired or a transition?
It's paired. So it's spin paired, meaning just that the spins are in opposite directions.
Okay.
There's really no connection to them. That's not, paired is kind of a bad word, I would think, because it implies a connection. But there's really no connection. It's just they're 2 magnets north to south. Okay. And so that's what we mean by spin. It's like the magnetic moment on that electron. And if it's north to north, they're unpaired. Just like magnets, you try to push 2 magnets together north to north, and they don't like it. If you pair them, then they'll snap together. Yes?
What's it shown as from the 1s2p to the 1s2s triplet? I thought that transition could happen.
It's forbidden by symmetry, but there's that dashed line. And so something in nature can cause that to happen, like a collision with a third body or something like that. So you can get the singlet to triplet transition, but not by light.
Okay.
Yeah. And so then you've got, you excite the electrons, so they're spin paired in the 1s, that goes up to the 2p, and then something happens, a collision or just some fluctuation in nature, and that electron can flip. And now you've got a triplet state. And it can get stuck there for quite a while until some other fluctuation in nature allows it to both emit and flip. And that's called phosphorescence.
Okay.
So we'll get to phosphorescence a little bit later in the broader category of electronic spectroscopy. But a triplet to singlet transition, radiative transition, would be phosphorescence. And what we're seeing in the long phosphorescence lifetime, I'll go ahead and tell you now, is that forbiddenness, right? So statistically, more than one thing has to happen, and so that makes it slower. So we're sitting there in that triplet state for like an organic molecule that phosphoresces. That molecule has gotten into a triplet state somehow, and it wants to emit light down to the ground state. Because remember, the lifetimes of electronic states are really short. But the lifetime of this triplet state, going back to a singlet ground state, is long. It could be seconds or minutes, and that's how our glow-in-the-dark stuff happens. So our Halloween glow-in-the-dark paint and the little spider rings and stuff that we have, those glow in the dark because of phosphorescence. So we charge them up, we get those molecules excited in the singlet state, they transition over to a triplet state, and they get stuck there. And then it has to just wait for some natural fluctuation to break the symmetry, and you can get the emission of light. So then they glow in the dark. So you've removed the source of light that's charging them up, and that lifetime is a long time, minutes, and so then it glows. So that's pretty sweet. Now, another thing for the Grotrian diagrams, you don't normally have, well, you don't. If you find one online or at the NIST Atomic Spectral Database, you will not have the electron configurations shown up here, in the diagram. What you have is this nomenclature down at the bottom. So look at this nomenclature down here. This is what you're going to be given by NIST. So let's try to understand that. Let's just pick this one right here, 1s1 ns1. It's sort of a generic electron configuration for that whole column. And you're looking at that column and you realize that column is a triplet column, so you know that the electrons are unpaired in that whole column. One's in the 1s and the other electron is in the 2 or 3 or 4 or 5s. So that's what the ns means. It's the first available shell. So we've got 1s, electron in 1s. What's the next n? The next one is 2. So it's 1s1, 2s1 would be the lowest one. And so this right here, the very first available n is 2.
That's because they're unpaired. They were
Yeah,
like,
if they were paired, it'd be 1s2.
1s.
Yeah. Yep. And then 3 and 4 and 5. So that's the electron configuration for that whole column. And the triplet means that they're unpaired. Now let's see. Yeah.
So in this case, is the second electron, so one's in the 1s, 2s, and then one's in the 1s, 3s for this diagram?
No, so you're naming two orbitals, and only one electron can be in one orbital. So this is for the whole atom. There's an electron in the 1s and an electron in the 2s.
And that changes depending on.
So in this column, then the next energy level up at a higher energy would be if that second electron's in the 3s.
So they're totally separate from each other.
Yes.
Okay.
Yeah. So every energy level is totally separate from every other energy level.
Okay.
Yeah, which is what's confusing. At first, like the Aufbau building up scheme, we like put an electron down here in the 1s and then up here in the 3d. And I kind of did that right here. So this right here would be the electron configuration if this is 1, 2, and 3, right? That's the electron configuration for this energy level. Yeah, so that energy level, if you were to kind of put those electrons in their orbits and show all the other orbital energies, then that diagram right there would fit for that single energy level alone.
Okay.
Yes.
Can both electrons be excited?
Yes, and there's, if you look at the Grotrian diagrams at NIST, they're pretty high energy. So above all of this would just be a mess of energy levels. And you click on one and you'll get the electron configuration that is that energy level.
Okay.
And you can have like a 2s and a 3d, even though the 1s is empty. Yeah. But those are really high energy, as you might imagine.
Mm-hmm.
Yeah. And so it gets really dense in terms of the number of energy levels up high. And those transitions would all be in the infrared or far infrared, maybe even the microwave region. So they're so close together that the electrons would hop around and they would just bounce around between the orbitals and try to find as low energy as they can. And so let's, before we start working on those term symbols, here's again some initial considerations. These mathematical sets deal only with the unfilled shells, the unfilled subshells. So if we're talking about carbon, we only have to deal with 2 electrons. Even though carbon has 4 valence electrons, we're only dealing with the electrons in the unfilled subshells. Really nice, right? So we don't have to deal, carbon has 6 total electrons, but we're only dealing with 2. It's a P2 system. Look at the periodic table and you see carbon where it is. It's a P2 system. So you should be able to look at these periodic table like silicon. Silicon is also a P2 system. 2 electrons in the P subshell, and that's the only unpaired electrons you have, or the only unfilled subshell that you have. And so you're just dealing with those 2 electrons. What atom would be representative of a D2 system? A D2 system. Yeah, titanium. So second column of the transition metals, that would be a D2 system, and then so would zirconium and hafnium and rutherfordium. Okay, so pull that out. And then the term symbols for the ground state atoms and then the filled subshells is all singlet S0. So if you had calcium, magnesium, beryllium, that whole column, that's a filled subshell, and so that's ground state term symbol is going to be singlet S0. But even the zinc, a D10 system, singlet S0. Everything's all paired up. It's a singlet. The angular momentum, the plus, the sort of, you think of angular momentum, the one spinning clockwise and the one spinning counterclockwise have canceled each other out. So L, capital L, the total angular momentum is 0. So that's an S, a capital S. And then L plus S and L minus S are 0 because it's 0 and 0. So if you have a filled subshell, that's the singlet S0 term symbol. So let's talk about this Clebsch-Gordon series. How's that a name for you? Clebsch. Yes. So it's 1, 2, 3, 4, 5, 6. It's a 6-to-1 consonant to vowel ratio. Okay. So anyway, it's pretty cool. So this capital L is the total angular momentum for the atom. and it's those electrons in unfilled subshells only, just emphasizing that. And so to come up with capital L for an atom, you look at the angular momentum quantum numbers for each individual electron that's in that unfilled subshell. So for carbon, which we will do in a minute, carbon, we have 2 electrons in the p subshell. And so we have each of those electrons. So what is little l for that? It's S, P, D, F. So S, P. So I always just do my fist is S, S, P, D, F. Those are my angular momentum quantum numbers. So S, P. So each one of those electrons has 1 unit of angular momentum. So little l's are 1 for both of those electrons because they're both in a p orbital. Okay. And so then we have this series. This is the Clebsch-Gordon series, which starts out with the maximum and the minimum. And so we'll practice with this. I'll go through it and then we'll learn by doing. Okay. And then we have the S, which is needed for the multiplicity, the capital S, and those are the spins of those electrons. And so we assume they're both spin up, and then this series gives us all the possible combinations when they're not both spin up. So you don't have to worry about saying, well, gosh, I assume they were both spin up. That's okay. This series calculates all the other possibilities. So we start with the maximum where they're spin up, and the minimum is when they're opposite of each other. So little s1 and little s2 for both of those electrons is plus a half. And so the maximum would be 1, and the minimum would be the difference between those two, which would be 0. So our capital S would have a plus 1 or a 0 as its two possibilities. And then you multiply by 2 and add 1 to get the multiplicity. And then this J is the total angular momentum quantum number. And this uses a scheme called Russell-Saunders coupling. There's also JJ coupling, which if you get into advanced inorganic and need that, then you'll have to learn that other way to do it. We'll just teach this one. This applies for most of the periodic table, like through the third row. And this, once you have capital L and once you have capital S, so the total angular momentum and the total spin, then you combine those. So this is how the spin interacts with the orbitals, and these are called spin-orbit coupling numbers. And so it's L plus S is the maximum value, the absolute value of L minus S is the minimum value, and then it's integers in between, or subtract 1 from max till you get to the min. And so this is how we write the term. We have the total angular momentum, which is L, the capital letter L. We have the multiplicity as a superscript prefix, and then a subscript added on is the J quantum numbers. So let's look at examples. So let's do some simple ones where we just have 1 electron, okay? Now the mathematical series are going to be boring because we just have one member of the set. Okay, so don't be confused just yet. We're just going to look at simple example first. So for sodium, we have the neon core, electron configuration of neon, plus 1 more electron, a 3s electron. And so that little l is 0. And so the capital L for the sodium atom is also 0, which gives you this term of a capital S. So in this case, we're talking about a term. The term is S, it's capital S. Now we're going to calculate the total spin. Okay. And so it's plus 1/2. And so in terms of this particular capital S, it's going to be plus 1/2, which is the total spin for that atom. And then 2s plus 1 gives a doublet. So we're going to have a doublet S term. The superscript prefix is going to be 2, and the capital S for our atom term. And now we do the coupling. So we have L plus S. L is 0 and S is 1/2. That's the maximum value. And then the minimum value is L minus S. So L being 0 minus 1/2 is S, but it's the absolute value in this case. And so in both cases, we end up with a 1/2. And so J is a 1/2. So this is our term for ground state sodium, doublet S 1/2. And the mathematical sets, again, were boring because we really didn't have multiple terms, okay, or multiple mathematical results inside the sets. So this is the same also for any NS1 configuration. So this is describing the electron cloud, and if the electron cloud for potassium or rubidium or lithium is the same as sodium, it's going to have the same description. Okay, so this is the same term for any NS1 system. Okay, let's now excite that atom by moving that electron to a p orbital. Things get a little more interesting. Okay, we have now an electron in a p orbital, so sp, L is 1. Okay, and so capital L is going to be p. Then we have the spin, still 1/2. Okay, 2s plus 1 is a doublet, 2. And now we actually have some items in our mathematical set here. We have 1 plus 1/2 down to 1 minus 1/2. And so this is 3/2 and 1/2. So those are our two terms, our J values for our terms. And so we end up with two terms in the excited state. We have a doublet P 1/2 and a doublet P 3/2. And this is just convention. Instead of saying 1 1/2, we just keep it in units of halves. So we have 3/2. You'll see 5/2, 7/2, 9/2 whenever we have these different J values. Now this is useful in spectroscopy. This is called a doublet because we have two spectral lines and they go from the excited states, this doublet P 1/2 and doublet P 3/2 down to the ground state of doublets S 1/2. And they're very close together. They're both, it's about 0.6 nanometers apart. And I need to bring the Cheez-It spectrometer down. Next time I'll do that. So this is a spectrometer I made out of a Cheez-Its box. And they used to have more sodium in these mercury lights. I think it was a contaminant, and they cleaned it up, upsettingly, because now I can't see sodium in my lights from my Cheez-It spectrometer. But you could look up there and you could actually see the splitting at 0.6 nanometers apart from a 50-cent piece of plastic stuck on a Cheez-Its box. Okay, so kind of cool. Now it's a special kind of plastic. It's been scratched to make it a diffraction grating, but that's pretty neat. So we'll have some fun with that. I'll bring it to class Friday. And then this is the Grotrian diagram from NIST. So this is the official sort of U.S. standard. That's what NIST stands for, National Institute for Standards and Technology. And you see the sodium emission lines. You see all of these different energy levels. So when you were asking about the different excitations, you can see a lot. It gets really dense up here. Mm-hmm. And then this is the ionization limit. So there you've yanked the electron completely off of the atom. And down here you see the different electron configurations. So this is what you would expect. It says 2p6 NS. And so what's your first available N after 2p6? Look at the periodic table. What's N, the first available orbital's principal quantum number? 3, yeah. So this would be 3s. 2p6, 3s. That would be 2p6, 4s. 2p6, 5s. 6, 7, 8, 9. Look how 8 goes all the way up. This is 2p6 NP. So that's what we were just talking about, the 3p electron. It's 3p or 4p or 5p. Now, this red line here, I clicked on that line and I got both of these guys here. So one is the doublet P 1/2 transition, and the other is the doublet P 3/2 transition. And you can see their wavelengths. They've got 7 significant figures on their wavelengths. So that's pretty good. So these are the terms for the ground state atoms for pretty much the first 3 rows that deal with JJ coupling. With Russell-Saunders coupling. And it gets pretty complicated. Look at this. This is a D4 system, a D6 system. There's no way I would ever ask you to do a D4 or a D6 or a D5, because I don't think I'll have the patience to do it. So every one of those Clebsch-Gordon series is nested for every 2 electrons. So you do them 2 at a time. So you take the first 2, come up with all your terms and so on, and then you take those net results and then add another electron and see how it couples. So think about what we're doing. So all the magnets of each electron and all the magnets of magnetic fields of the orbitals, and we're doing it pairwise and coming up with all the possibilities. So it's really very tedious. And so you have, quintet D, triplet H, triplet G, F, and so on. And that's one thing I didn't show you on this last Grotrian diagram over here is 2p6NH. So that's an electron in an H orbital. That's an electron in an I orbital. Okay, so yes.
Are orbitals like essentially infinite? It's almost
Yeah, it just gets more and more angular momentum, and it just starts to look like a koosh ball. Remember a koosh ball? It just had all these little fibers coming out. Those are all the lobes and nodes, and so it just gets incredibly complex. Yeah. So there's really no limit to how much angular momentum you could put into an orbital. So we really only deal with up through F in ground state or near ground state atoms, but they go up pretty high. And you can see what those transitions would be. There would be, deep UV transitions. So let's do some more practice. Let's do carbon, and that'll be fantastic because it's a P2 system. So the electron configuration for ground state carbon is helium core, 2s2, np2, that N would be 2, so 2p2 for carbon. We're just dealing with those last two electrons because those are the ones in an unfilled subshell. And so this is the Clebsch-Gordon series. The capital L for the whole atom takes into account the orbital angular momenta for each of those electrons. And we go from the max to the min. And so what is L for each of those? Remember SP. So there's 1 for each one of those. I'm going to see y'all on the exam going. Okay, great. So this is L plus, so it's 1 for each of those. So these are 1s. These are L's over here. These are 1s over here on the right. So it's 1 plus 1 is the max. 1 minus 1 is the min. So it's 2 and 0 for the max and min. And we subtract 1 from that max until we get to the min. So if a max of 2, min of 0, the middle term is 1. So it's 2, 1, 0. So those are the 3 terms that we're going to have. We're going to have a D term, which corresponds to the 2. We're going to have a P, which corresponds to the 1, and an S that corresponds to the 0. So that's where the big capital letters come from for the whole atom. Then we have the spins of those electrons. Again, they can be plus 1/2 each. So that's the max value. So the max value is 1/2 plus 1/2, which is 1. The min value is 1/2 minus 1/2, which is 0. And so these are going to give us our superscripts once we multiply them by 2 and add 1 to get the multiplicities. So when S is 1, 2S plus 1 is 3, which is a triplet. So we'll have triplet D, triplet P, triplet S. And then we'll have, when S is 0, 2S plus 1 is singlet, so we'll have singlet D, singlet P, singlet S. Notice how each one of those multiplicities goes with each one of the terms. So we have 6 terms possible. So these are the 6 terms that we have. So the Clebsch-Gordon series helps you build up the full set of terms. And now we need the subscripts, those J values. And we take L plus S for each of these situations. So for a particular term, like this one, we have L, which is 2, and S, which is 1, because 1 will give us a triplet. Okay, so L plus S and L minus S is our full range. So now we do the Russell-Saunders coupling with each one of these 6. So it's just a nested problem. That's why I said I didn't have the ability to do a D4, because I'm just not that meticulous. So for the triplet D, L is 2 and S is 1. Now, if I gave you that triplet D and asked you for L and S, you should be able to give it to me. Okay? So this is where you need to really focus on how you build these terms up, and you've got to be able to go backwards too. I say, okay, triplet D, what is L? Capital D, S, P, D, L is 2. And then the triplet, if I see that, what is S? Well, 2S plus 1 equals 3. Subtract 1, divide by 2, I get to 1. So then the J values are 2 plus 1 down to 2 minus 1. So 2 plus 1 is 3, 2 minus 1 is 1, and you subtract 1 from the max until you get to the min. So 3 minus 1 is 2, 2 minus 1 is 1, so that's the full set. So we have then a triplet D3, a triplet D2, and a triplet D1. Now for the singlet D, J is equal to 2, L is equal to 2, S is equal to 0. And so 2 plus 0, 2 minus 0 are the same. So your max is equal to your min. You just have one item in that set. So it's a singlet D2 would be the only pieces in that, that particular part of our term symbols. It would be a singlet D2, and that would be it. And then for the triplet P, L is 1, S is 1. So for the J values, it's 1 plus 1 all the way down to 1 minus 1. 1 plus 1 is 2, 1 minus 1 is 0. Subtract 1 from 2, we get 1. Subtract 1 from 1, we get 0. So that's the full set. So we would then have a triplet P2, a triplet P1, and a triplet P0. Then for the singlet P, it's 1 and 0. So we have 1. And then for the triplet S, L equals 0, S equals 1. So the J values will be 0 plus 1 and 0 minus 1. We never have any negative numbers in this. And so in any of these cases, always remember the minimum is going to be an absolute value. So there's only going to be one item in that set. So we'd have a triplet S1. And then for the singlet S, everything is 0. So we'd have a singlet S0. So these are all of the terms for a P2 system. Not just carbon, but also silicon. Okay. But that's everything. And that's how you're going to label the energy levels in atomic spectroscopy, is transitions between these different atoms. And so here they are. This is the table from the NIST Atomic Spectral Database. And the energy levels are given right here in wave numbers. And here's the 2s2, 2p2. It's a triplet P0. That happens to be the ground state. And there's only one ground state. So that's the lowest energy electron configuration for carbon. You could still have that same electron configuration, but remember the M sub L quantum numbers? You can put those electrons in the px, the py, or the pz. One of those has a different M sub L than the other, and it's going to interact with that in spin-orbit coupling and give you a slightly higher energy, and that would be this triplet P1 term with 16 wave numbers above the ground state. Not very much at all. And then the triplet P2 would be 43 wave numbers above the ground state. Then we have all those other terms that we just discovered. The singlet D, the singlet S, the singlet P, the triplet D, the triplet S, the triplet P. So, and these are all of their energies. If you took differences between these energies and used the selection rules, you would get all of the spectral lines for carbon. And carbon is going to be much more complex than hydrogen or helium because it's got two unpaired electrons in that P subshell. And so it gives you a whole lot of terms and a whole lot more transitions. Let me pause there because that's kind of a stopping point. Review this, work on some of the problems. Next time at the beginning, I'm not stopping today, so don't pack up. But I'm just saying, be able to go forwards or backwards on these terms. Let's look at Mercury real quick, just to show you that here's Mercury. So this is the Grotrian diagram for Mercury. Here's the spectrum for Mercury. So this is what's coming out of your fluorescent tube lights. And these have some interesting configurations down here. Look at Mercury on the periodic table. Okay, it looks like a D10 system. And so 5D10, 6S, NS. And so it's actually exciting the S electron, not the D electron, in this column. And so that would be 6s ns. Well, you can put two electrons in the 6s orbital. So this first one would be 6s2. So 5d10, 6s2, that's what we would say is the ground state Mercury electron configuration. But look how much lower this one is. It's kind of unusual. Okay, this is a 5d10, 6s np. And so it's actually lower in energy to have an electron in that p orbital. So that 6s, sort of the barium electron, is put in that first orbital on the p, and that's actually lower for Mercury. So am I going to ask you for the Mercury electron configuration? Probably not, because you'd have to know this information to know what the ground state Mercury electron configuration is. I would have said it's this one, that it's the 5G10-6s2. But you get that far away from the nucleus and the orbital energies are so close together that this stuff might occur. You have F orbitals, D orbitals, and so on. So you can look at these electron configurations in the bottom of these Grotrian diagrams and learn a lot about the atoms. Let's look at, so here's the electron configurations for all of those. Last thing to end with is, here's, oh, stop. Go back. So right here, even in a complex atom like Mercury, this is the electron configuration for the lower state. This is the electron configuration for the upper state in a spectroscopic transition. What do you notice? Look at the last letter in each of those columns. Can you see the selection rules?
1, 3, or 5.
Just look at the letters, though. I have a P to S. I have an S to P. P to S. P to here's one that's a P to P, but almost every one of these others. Here's a D to P, P to D. One change in angular momentum still. Okay, so the overarching selection rule, even for an enormous atom like Mercury, is still delta L equals plus or minus 1. We're jumping either from an S to a P orbital or P to a D orbital. If we didn't have that restriction, our atomic spectra would probably be opaque because we would have so many more allowed transitions than we do. So it's really interesting. This conservation of angular momentum has really opened up atomic spectra, opened up the universe for light to travel long distances because most of the transitions are not allowed. Great. I'll see you next time.